Hi everyone, my name is Georgia, and I'm excited to present our new CVPR paper on learning 3D object shape and layout without 3D supervision. This is joint work with Nikhila Ravi and Justin Johnson. The goal of our work is to build a model that from a single image of a complex scene can predict all the objects in the image, their 3D shapes, and their 3D position, and all this without direct 3D supervision. Our work belongs in the family of object recognition. In the past, we have built models that understand objects from images by predicting their object types and 2D silhouettes like Mask or CNN, or predict 3D object meshes like in Mesh or CNN. But scenes are composed of 3D objects laid out in 3D space. So in addition to 3D shapes, can we also predict 3D layouts and all from a single image? Mask and Mesh or CNN have been successful thanks to supervised learning and annotated datasets. But in the case of 3D, collecting 3D annotations is very expensive. So supervised learning does not seem like a viable path for 3D object recognition. So we propose to bypass the need for 3D supervision and leverage multiple views, for example, video frames, and also 2D object annotations, which we know are easier to collect. So during training, we assume that we have 2 or more views of a scene, which can come from a camera rig or different frames of a video. We treat the first view as input, while the second view is a target view. Our model is heavily inspired by our prior work, Mesh or CNN. The input image is encoded by a backbone network, which predicts regions of interest or ROIs. For each predicted ROI, the model predicts its object type and refines its 2D box, just like faster RCNN. A new head, which is called layout head, predicts the object's distance from the camera and its depth extent. And a shape head predicts the shape of the object by deforming a sphere mesh. Notice that we could replace meshes with any other representations, including implicit ones like SDFs. Here, we choose meshes because they're fast, and efficiency is important, as we will be dealing with complex scenes with tens or hundreds of objects in them. So this is repeated for each ROI and results in a predicted 3D scene. Now remember, we don't have 3D ground truth to supervise our model's output. So during training, we leverage multiple view supervision and render the scene from a given novel view, and compare the object renders to the ground truth target annotations. The target view and its object act as a training signal for our model and are used only during optimization. During test time, our model infers a 3D scene from a single image. So during training, we extract the object information from the target image, either using ground truth annotations or a pre-trained Mask or CNN model, which serves as a generator of proxy ground truth. We also link objects in time, which we do either using ground truth information or simple tracking heuristics for videos. Our experiments show results with both ways of extracting the necessary 2D information, either by ground truth or off-the-shelf object detectors. We call our model USL. USL inherits the 2D losses from faster RCNN. But what are the appropriate losses for 3D layout and shape prediction? To answer that, we need to understand what our model is tasked to predict. USL needs to predict the 3D layout. Here is what the model's layout prediction looks like during training. We show the input image to the model on the left, and the ground truth RGB and object instances of the target view on the right. In the middle, we show the predicted object instances rendered on the target view. So as the model figures out where to place the objects might appear anywhere in the target view. The same holds for shape estimation. As the model figures out what the right shapes are, the objects can take any shape. We define a training loss that captures errors in shape with a pixel-wise cross-entropy loss, and errors in layout with a distance transform, such that useful signal propagates through the model when objects appear anywhere in the target view. You can find more details about the implementation of these losses in our paper. And there is another important model detail. Remember RolAlign, which was a core contribution of Mask or CNN and which is responsible for pooling features from the regions of interest. This happens right here in the model. RolAlign is translation equivariant, which made it so effective for 2D object detection. But it does not maintain information about an object's scale or aspect ratio, as it warps the region to a predefined square resolution. Now, 3D recognition is a contextual task, and an object's dimension and size are telling about its placement in the 3D scene. Equivariance with scale and dimensions are important properties for 3D. So we replace RolAlign with ROI map, which directly pulls from the bounds of the ROI and does not resize the features to a fixed dimensional representation, and thus is equivariant in all three sources of variation: translation, scale, and aspect ratio. Okay, time to see some results. We experiment on 3 video datasets, one simplistic one based on ShapeNet, and 2 more complex ones with realistic multi-object scenes. Here are some results on our ShapeNet dataset, and a comparison with the supervised measure CNN, which trains using direct 3D annotations. Even though our approach is not supervised in 3D, it's able to capture both 3D shape and layout. Now let's turn to the more challenging Hypersim, one of my favorite datasets from the past year. Hypersim, though synthetic, is very challenging. It contains over 450 very diverse scenes, including warehouses, churches, lofts, restaurants, etc., with many objects per image. The dataset provides images of these scenes, examples of which are shown here. For context, masked CNN performance for 2D recognition on Hypersim is 25 points lower than on COCO. And here are results produced by our method on novel scenes from a single image. We also evaluate using multi-view silhouette intersection metrics, which we show to be approximate 3D metrics in the absence of 3D ground truth. ROI map is indeed important, which verifies our intuition for building in equivariance in all 3 axes of variation. Using a distance transform to capture layout errors is also impactful. In summary, I presented an unsupervised approach for 3D object understanding from complex scenes with multiple objects, and which is scalable to many videos during training. Of course, there are limitations. As you might have noticed already, the predicted 3D shapes are coarse. This is not a surprise, as we learn through shapes only through 2D object silhouettes. Shapes could be improved if we also learn through texture. And finally, we assume static scenes. Our model can be extended to tackle dynamic scenes if we model shape, layout, and motion jointly. We believe that addressing both of these limitations are exciting future directions. Thank you very much for listening, and you can find more details about our project in the project webpage.